linear. In our example, it has 3 branches. And this port is terminated with a capacitor, and we have the usual equations for port voltage, capacitor voltage, port current, capacitor current, and more important, the relation between capacitor current and voltage. And we know, of course, that the current is equal to capacitance value times the time derivative of the voltage across the capacitor. Let us assume that we start with our circuit at time 0 with a certain initial voltage of the capacitor, which I have chosen here to be equal to 6 volts. And then we can check in which direction the voltage across the capacitor will evolve. Will it go in this direction or will it go in this one? Well, from having this positive voltage across the capacitor leading to a positive current due to the piecewise linear characteristic, a positive current of 2 amps as the port current gives us a negative current through the capacitor, and the negative current through the capacitor gives us a negative time derivative. Therefore, the voltage across the capacitor has to decrease, and therefore our dynamic route is in this direction. We are moving from point P0 away in this direction. And as long as we are still on that branch, it's simply as if we would have a affine line here with a open circuit voltage of 4 volts and a slope of corresponding to a conductance of 1 Siemens or a resistance of 1 ohm. And that is, for this part, the equivalent circuit which we have. That's our open circuit voltage of the 4 volts, 1 ohm, and we have decided that the capacitor should be 1 farad in order to have very simple numbers. And then we can simply evaluate the evolution of the voltage U over time t according to the general solution for first order linear circuits with constant excitation, where the constant excitation is the 4 volts here. And plugging in all these numbers, we come up with this evolution over time. And now the interesting thing is to compute the time t1 at which the capacitor voltage has decreased so far that we are now at point P1, at which we again have to look and to make a decision how the further evolution will be. Current is still positive as the port current, still negative as capacitor current, therefore still the time derivative will be negative, capacitor voltage will decrease further, that is, we're going this way to point P2. Well, now we have this affine line, and for this affine line we again draw a equivalent circuit here. Now the open circuit voltage is 6 volts and the slope is minus 1 ohm. Capacitance is still 1 farad, that hasn't changed. Well, we again plug in these numbers into our general solution, the green one here, and end up with this equation. And now we are looking for time t2 when capacitor voltage has actually achieved the value of 3 volts. We plug in the 3 volts and now compute the time t2 and find out that time t2 simply is almost 1.8 seconds. Well, and now we are entering the 3rd branch and the last one in this case, where the open circuit voltage now is simply 0 volts, because it's not an affine but a straight line through the origin. Again, we have a slope of plus 1 ohm and compute the evolution over time and find time t3 when we have reached point P3, and that is time towards infinity. And putting everything together, we get the total evolution of the voltage across the capacitor over time as 3 segments. They're all 3 exponential functions, one decaying, one increasing, and other one decaying again. So basically, it's again a circuit where you had always linear first order and constant excitation, which is a rather simple situation. The main complication here was the time windows during which such a equivalent circuit is valid was not given to us by some higher power, but we had to determine it by computing the certain time instances when we have reached these points where the slope of the piecewise linear characteristic changes. Now we will, schalten Sie mir bitte die Tafelbeleuchtung ein. Nun wollen wir das anwenden auf eine wirklich interessante Schaltung, die ein Zusammenführen von wiederum von Dingen, die wir schon im Wintersemester gemacht haben und jetzt eingebettet in das Rahmenwerk der dynamischen Schaltungen ist. Wir beginnen zunächst mit so einem negativen Impedanzkonverter, wo wir einen